Great. Yeah, thank you for opportunity to tell you about some improvements to software for GWAS and polyploids. We're going to start off by talking about the GWAS poly software, which I presented on more broadly at our workshop last year. So I hope if you're new to it, you've had a chance to at least look at that video, because I'm not kind of going back to basics here. And it's available on GitHub from this link. And what I want to talk about today is then some updates that were made in the past year. And there you can see the highlights here. The first update will be describing what's called the Loco method for calculating kinship in a GWAS. The second update will describe new functionality for estimating a partial R squared in multiple QTL models. And then lastly, the ability to use VCF marker data with this new function VCF2 dosage. Okay, so let's get into it. Another change compared to last year is that the example data set in the vignette is improved, or larger at least, compared to the original vignette. So the original data set that came with the publication from 2016, I mean, the data set actually is at this point close to 9 years old. And so I felt it was worthwhile to use a newer data set that's a bit more representative of the kinds of GWAS panels that people are looking at now. So it's quite a bit larger. It's close to 1,000 individuals. It has they're tetraploid potato samples. There's about 10,000 markers from a SNP array. It spans multiple environments. So when you read the data in, you'll get this message about detecting the following fixed effects. So you have additional columns that can be covariates or cofactors. And the way the software knows that is because you've told it how many traits to expect. So it's only looking for one trait, and then everything else it finds, it assumes is some kind of fixed effect. This is unlike the original data set, which spanned multiple market types. This is actually all potatoes from a single market type. So a little bit less diversity from that point of view. One thing that I wanted to, it's a very slight tweak, but something that I think is worth mentioning is just providing some recommendations about how to curate markers as it relates to rare alleles. So GWAS relies on linkage disequilibrium, or LD, between markers and QTL. One of the simple mathematical prerequisites for a marker to have high LD with a QTL is that they have to have similar frequency. And that alone doesn't guarantee that you have high LD, but if you don't have similar allele frequencies, it's a mathematical possibility that you could have high LD. So reasoning from that, we know from principles of statistics that statistical power, meaning the probability of detecting a QTL, is low for a rare allele. So if your QTL has a low minor allele frequency, or MAF, you're going to have a hard time finding it. And markers that have low minor allele frequency, all they can be potentially good for is detecting QTL with low minor allele frequency, which I just mentioned is difficult. So the bottom line is that there's incentives to remove markers that have low minor allele frequency, because one, it reduces the computational burden. You have fewer markers to test, and the fewer markers you test, the less you have to adjust your significance thresholds to account for the multiple testing phenomenon. So I think that's probably something that most of you maybe are already familiar with, but then getting down to actually how you do this in the software, the function that was created to do this is called set params, which does not only this, but a number of other, sets a number of other parameters that dictate how the model is constructed. There are two different ways that the software allows you to do this curation, removing of rare alleles. One is based on minor allele frequency, or MAF. The other one is based on the maximum genotype frequency, which is sort of specifying the complement of the minor allele frequency. It's the maximum frequency of the most common genotype. And so, in terms of what you should be thinking of pictorially, here's like a histogram, right? You're going to have, let's say for a tetraploid species, you'll have these 5 different genotype classes. What is the most common value? In this case, the dosage of 4 had a frequency of near 0.5, which is fine. This is still plenty polymorphic for a good to include. But you can get markers that you could have 99 or higher % of the of all the samples, let's say, have the same dosage, which is really not enough variation to bother including in the test. So based on some 2-sample t-test kinds of calculations, I've kind of recently come up with this own rule of thumb that I tend to use, which is that the maximum genotype frequency should be less than 1 - 5 over the population size. So the way you would set that in this situation, you can just see the population size when you load the software, load your data set, or otherwise you've investigated that. If you don't specify a minor allele frequency or a genotype frequency, the software now will impose one for you just as a default behavior. It didn't used to do that. It had a more generic way of doing it. So anyways, now if you don't specify, it will use this, but I would encourage you just to think about it yourself. And if you like this recommendation, use it. And if not, use something else. Okay, so now coming to the Loco idea, which is a clever acronym for leave 1 chromosome out. And the background here is that the traditional kinship matrix that was originally proposed for mixed model analyses of GWAS, in that approach, the significance of a given marker to compute the p-values that you see in the Manhattan plot involves including the marker as a fixed effect in your model. Using a kinship matrix is equivalent to including all of your markers as random effects as the genetic background. So the net effect is that when you test the marker, it's present as both a fixed and a random effect. Listgarten et al. Were the first to really point this out in a publication and showed that through simulation, this leads to a slight reduction in statistical power. They used some clever linear algebra to get around it, which is not that easy to implement without rewriting the entire foundation of the software. So a simpler fix to the problem was proposed by Yang et al. In 2014, in which they just advocate calculating a separate genomic relationship matrix or kinship matrix for each chromosome. And the kinship you calculate for this chromosome is based on all the markers except those on that chromosome. This ensures that you don't include the marker as both a fixed and a random effect in the test. So when you run the command that does this in the software is called set.k, and now it has this additional argument that's called Loco. For a little while, I went back and forth about what the default behavior should be. So it could have been Loco equals false, would reproduce the original behavior of GWAS poly. And for a time, I wrote Loco equals true as the default, and I got some people emailing me trying to figure out why they were getting different results. So I've just now changed it so there is no longer a default. You have to, again, specify, do you want Loco equals true or false? And that way, at least as a user, you're aware of what kind of analysis it's doing. So here's a comparison. I'm going to run that, and then this compares the little snippet of code, shows we've got 2 different variables, one original, one Loco. And then if we continue with the analysis and run the Manhattan plot, here is the result. So this is for the trait that comes with the data set, the vine maturity in potato, which we know already of this major gene on chromosome 5. And we can see that what looks like we're getting a higher peak with the Loco model. The most significant SNP is closer to 25. And we also get a little bit higher results for these minor QTL, one on chromosome 9, and then this one on chromosome 4 finally squeaks above the threshold. So we actually detect 3 QTL with the Loco model compared to just 2 QTL with the original model. One thing to keep, so this is what you would expect based on literature. However, if you look at this, and I'm not showing you the QQ plot, but you can kind of also just see it by looking at the general level of all of the background. You can see it's a little bit higher actually. So there is actually slightly higher inflation of the p-values across the genome. So I haven't really done a full-blown power test to verify the results of Listgarten et al. I'm just taking them at their word that there still is a slightly higher power from using the Loco. One other benefit of Loco comes into play when we start to try and estimate partial R squares. But as a prelude to that, I wanted to just call your attention to this new function also. It's called LD plot, which provides a plot of the average R squared versus genetic distance, for which there's other software you can do that, but this way it does it in-house. The practical consequence of knowing this information is that you could potentially use it, for example, to prune your list of significant markers. So here's the result of that plot for this sample data set, which shows that certainly by 10 megabases, the R squared has sort of hit the plateau level. And however, remember, this is just an average. There's a lot of variation around this. So you want to be maybe a little bit more conservative when you try to specify a threshold. And in this function getQTL, which is designed to take your result after you run the genome scan and then just return all markers above your threshold, you can now, if you have a lot of markers, you'll get a lot of markers in the output above your threshold. You could have 25 markers or more in a peak. So now you can specify, okay, I want to only pick, let's say, one marker, the most significant marker within a certain window. And that window, again, would be one way to determine it would be by looking at this LD plot. So if you use, in this case, I'm using 5E6, that means 5 million base pairs or 5 megabases as my window. The output is these 3 QTL. You get one marker for each, tagging each of the QTL that we just talked about on the previous slide, chromosomes. 5 being the most significant one, and then 4 and 9 being more minor. So in the getQTL output, what you get is the score, the minus log 10p. You also get this estimated effect size, which is basically the fixed effect estimate from the regression model, from the mixed model. And what you don't get is an R squared, and many people have asked for that. So that's really what this next function is designed to do. It fits a model with all of the QTL that you specify, and then one at a time it removes the QTL and tests their significance under backward elimination. And it uses the likelihood ratio to then compute what is the R squared under the backward elimination. Because basically the QTL discovery is essentially a forward entry procedure. If you're familiar with basic principles of multiple regression, you test every predictor on forward entry and then also make sure it's significant under backward elimination. So this is the backward elimination part of that process. The argument QTL should be a data frame with the marker name and then what model you want to include it under, your additive or the different types of dominants that are present. And then if you have fixed effects in your data set, you need to specify again how you want them to be included so that you can see more information about the syntax in the vignette that illustrates this. So in this particular example, the output from FitQTL is now the p-value under backward elimination, which is so small that it doesn't even register, it's 0. And then this partial R squared. So 8% of the variance is explained by the chromosome 5 QTL, and then about 2% for the ones on 4 and 9. If you had included multiple markers tagging the same QTL, which I didn't in this example, you would find that a number of them would not be significant. You would see p-values here that would lead you to potentially reject them in the multiple QTL model. So the advantage of that is if you, for example, think you may have multiple QTL in close proximity to each other, then trying to figure out exactly how many markers you should include becomes a little bit, more exploration is needed. So the p-value argument here can come into play if you're looking at a situation like that. Just looking at my time here. Okay, so the next innovation that's available just as of a week ago is the variant call format option. So VCF is a common format for GWAS data, and this new function doesn't directly read the data into GWAS Poly. It just converts a VCF file into the file format that GWAS Poly expects. And there are many different ways that genotype information can be represented in a VCF. And at present, there are 2 different what are called the format fields. that the software will recognize, and you specify when you call this function. The first one, GT, refers to the posterior maximum call, and that's what looks like this slash separated set of 0, 1 digits. It's a binary representation of the genotype. And another option is the DS field, which is the code that's used if you have a posterior mean. And if you're dealing with a situation where you have somewhat lower read depth and there's quite a bit of uncertainty, or in other words, a low genotype quality score, I would encourage you to use the posterior mean, which is something we have talked a bit about in last year's meeting. PolyRad already has some functionalities for doing that, and you can get that from other software as well. So using the posterior mean will give you a fractional value of dosage, but then that helps to account for the uncertainty in the additive model. So here is what the syntax looks like. You've got the name of the input VCF file. The second argument is the name of the output file that is going to be created for GWAS poly, which genotype code you want to use. And then there's these diploidy, and then these three last arguments are used to control. Basically, you can do some filtering of your variants on the fly right before you even get to the GWAS poly, which is in many cases needed because you may have whatever you use to generate your VCF may have done a very light filtering job. So for example, what is the minimum sample depth that you want to impose in order to even make a genotype call, right? I mean, we've talked before about how for, let's say, a tetraploid, for example, you need at least 50 reads to have a GQ score, let's say over 10, meaning having less than 10% error for a duplex genotype call. But if you're willing to use the posterior mean, you could certainly get by with less than 50 reads. And I would encourage you to do that because there still is some information there. You just don't know if it's a 1 or a 2 or 2 or 3, but you know it's not 0, for example, or 4 if you're talking about a tetraploid. So anyways, you can play around with what minimum sample depth you want to use to make a genotype, include a genotype call in the output file. You can modulate the maximum proportion of missing data for that given marker. And then also, what is the minimum number of samples with the minor allele? This is similar to a minor allele frequency. It's not really the same. It's a slight variation on that idea, but can also dramatically reduce the number of variants in your VCF file if whatever you use to generate it might have had a very low threshold for what's output there. So based on some previous conversations, I reached out quickly to Oscar's group at Texas A&M and asked if they could share one of their GBS data sets, which they already had in a VCF. So this is a tetraploid Rose F1 population. So it's not really the typical population you would use for GWAS analysis, but you certainly can analyze an F1 population using GWAS methods. And of the 80,000 variants in the VCF file, after using those filtering parameters I just showed, there were 45,000 exported for GWAS poly. And using a phenotype for disease resistance, we're seeing clearly the detection of the gene on chromosome 6, which is what they were expecting. So this software, this VCF2 dosage function has not been extensively tested beyond this one example. So I hope some of you will try it out and give me some feedback if you find errors or have suggestions for improvement. Okay, so turning to some other topics related to improvements for GWAS. The next topic touches on the question of how to best analyze data sets that span multiple environments. And when doing GWAS, we ought to be analyzing data that span multiple environments. That ensures that the QTL or QTN that we discover are robust and meaningful across more than one environment. If you're going to use something for breeding, you'd like to know that has explains a significant percentage of the variation across more than just one environment. So you can use multiple environment data in GWAS poly using cofactors, like I just showed in the vignette, where it would detect an environment variable, for example. And you can have other fixed effects, but it doesn't have much sophistication in terms of modeling more complex types of experimental designs, where you might maybe need different types of random. It can't include random effects beyond those that it already knows about for markers. And it, for example, can't model different types of spatial variation So it's just limited in terms of what kinds of experimental designs you can use. And this is not, a unique limitation of GWAS poly. I would say this limitation is common, that many times specialized software for these types of analyses has some limitations. So people often will do their analysis in 2 stages. They'll use a more general purpose software for mixed models to analyze each environment separately and computing a BLUB, or best linear unbiased estimate for each genotype as a fixed effect in each environment. And then in stage 2, they will combine all the BLUBs across the multiple environments. That's the response variable. And now they do the GWAS using, let's say, environment as a fixed effect. And the more sophisticated analyses were already taken care of in stage 1. So that's certainly how I would recommend, if you were using GWAS poly, that's how I would recommend analyzing a multi-environment data set. The problem is that the BLUBs you calculate from stage 1 will typically have different standard errors associated with them, because you may be dealing with unbalanced experimental designs, meaning different numbers of replicates for the different genotypes, and that information can be lost. You may also just have fundamentally different plot heritabilities in different environments. If you had a lot more residual error one year than another, that information is not propagated if you only consider the BLUBs. So there's been kind of a shift in terms of what's really considered best practice in the analysis of this kind of data sets in plant breeding and genetics. And if you're just hearing this for the first time, I would encourage you to look at some of the recent literature. And one of my favorite papers is this paper by de Messa et al. 2017. De Messa was a graduate student in the group of Professor Hans-Peter Pifo at the University of Hohenheim. And what they show here is that basically you should try to propagate the uncertainty from your stage 1 estimates into stage 2, and that leads to what's called a fully efficient analysis, meaning that it's as good as if you could do the analysis in a single stage. Now, you can't do this propagation of uncertainty in GWAS poly, but you can in a package that I've been working on for the last year, in which you're going to hear a lot more about tomorrow. The package is called StageWise. I'm bringing it up now because it also does have the ability to do a GWAS, even though it's not as extensive as a functionality as what GWAS poly can do. So in the StageWise package, which is also on my GitHub site, there are 3 vignettes, and we're going to be going through those in more detail tomorrow. What we're going to focus on right now is the analysis of a single trait under the assumption of homogeneous G by E. That means that you assume that the genetic correlation between your environments is the same, which would be a reasonable assumption, for example, if you had multiple years of data at a single location. And that's the kind of data set that's used in the first vignette. Here's an overview of the 5 functions that are in the package, which we're going to go through in more detail. So the package starts by using the function called stage 1, which, as I just described, is designed to analyze each environment separately, computing the BLUBs for genotype, and in this case also their uncertainty, which is represented in the variance covariance matrix for those BLUBs. At the same time, you need to import the marker data, and it computes what we'll call a G matrix, typically in in the context of genomic selection, which is the same thing basically as the K matrix in GWAS. Those 2 pieces of information combine in the function stage 2, which is an elaborate set of wrappers around calls to ASRemal-R and interpretation of the results from ASRemal-R. So you do need a license for that software to estimate those variance components. The information in terms of the variance components and the stage 1 BLUBs is then fed into this BLUB prep command, which is really just a intermediate command to do the expensive part of the calculation, which is the inversion of the full variance covariance matrix. And at the same time, you can choose to mask the certain BLUBs from stage 1, which allows you to explore a variety of cross-validation schemes. And the reason to do that is that you only have to do it once, and then you can run this BLUB command and basically look at a lot of different results rather quickly. You can, for example, compute the BLUBs of the markers themselves, and by standardizing them, you get GWAS. You can also compute the BLUBs for the individuals, and then you get breeding values. So what we're going to talk about right now is the standardized marker effects to compute GWAS scores. But before I do that, I guess I have a slide just showing you the benefits of the fully efficient model, which means if we call stage 2, On the left-hand side, we include the blues from stage 1 and the marker data. But on the right-hand side, we have this additional argument VCOV, which stands for variance covariance matrix. So by including those uncertainties of the blues from stage 1, we can see that we've dropped the AIC by about 100 points. It's like 46.67 on the left, then 45.68 on the right. So we've dropped the AIC by about 100, which is tells you something about that it's doing a better job of explaining the data relative to the number of parameters that are being estimated. You also can see partitioning of variance here in these two outputs. When you include the variance covariance matrix from stage 1, you're able to separate the G by E from the within environment residuals. Anyways, the main point here is to get on to talking about the BLUB. So this uses what is a fairly new concept. It's only 5 years old or so that a set of scientists in animal breeding realized that standardizing marker effects by BLUB actually produces the same statistic as standardizing them by BLUB. Under both scenarios, they are standard normal random variables. And the way this is done in the package is you call the BLUB command, you say what equals marker, and then you can tell it how many cores you want to use. And that's the indication to it. It should do this standard error calculation, which takes a bit more time than just simply computing the BLUBs of the marker effects themselves. And there's a function for making a Manhattan plot. And you can see we get something that looks, this is the same data set that's in the GWAS poly package, and we're detecting those results on 5 and 9, but not the smaller one on chromosome 4 that we found with the Loco model. You can also include then the results that you would find from your GWAS. The main practical reason to have that in this stage-wise is that when you want to then start to understand, let's say, partitioning of variance or make predictions, you can go back and include markers that are detected as having a large enough effect that you want to include them as fixed effects. And we can now see, for example, what the contribution of the chromosome 5 QTL and the chromosome 9 QTL, it's about 10% and 3% of the variance. So similar to the estimates that we saw from the fit QTL function in GWAS poly. Okay, so summing things up, this stage-wise package has the advantage that it makes the most efficient use of the data in the context of a two-stage analysis. But on the other hand, it really was never designed to be a full-service GWAS package. It will only test the additive QTL model, whereas GWAS poly has a series of dominance models that you can and even a general model that you can test. There's not as many options for detection thresholds. So again, choosing which one best meets your needs could vary depending upon your situation. Both packages estimate partial R squared. GWAS poly uses what I will call an exact calculation based on maximum likelihood. Stage-wise uses a more approximate method just based on ratios of estimated variance components, but it has the advantage that it's going to give you a more complete breakdown of the variance across multiple kinds of fixed and random effects. So things that didn't happen in 2021 that are still on our to-do list is being able to extend this to multi-allelic markers. And now that we have the VCF2 dosage functionality, that's going to be a high priority. And then also the analysis of data sets with mixed ploidy. So stay tuned for that a year from now. Thank you.